The use of hydraulic systems has increased the productivity of all modern equipment. Hydraulic systems allow operators to control enormous amounts of mechanical energy and to perform large work tasks both quickly and economically. With proper maintenance, power equipment will provide many hours of service with little or no costly downtime. When service is required, problems that occur are easily handled when the technician uses the right diagnostic methods and tools. Hello, I'm Doc Kubota, and welcome to the Kubota Service Pro Tractor Series. Hydraulic systems provide a challenge to the professional technician. Modern hydraulic circuits incorporate logic to protect the operator and machine. When these systems need repair, proper diagnosis is the key to reducing downtime for equipment operators. Misdiagnosis is a major problem that causes significant financial loss and extra downtime each year. In one warranty case, the technician's initial diagnosis on a loader with a slow cycle time was a bad pump. After he changed the pump, the machine's performance or cycle time improved only slightly. The technician then replaced the loader control valve, which fixed the problem. The total cost of the repair exceeded $800. After testing the components and inspecting the service records, Kubota's warranty department found no problems with either the pump or control valve. The system cartridge relief valve was finally found to be faulty. With the proper test equipment and diagnostic techniques, the technician could have quickly discovered the problem and repaired it. The cost of this bill was excessive. It was unfair to the customer and the dealer, who had to absorb the difference in the warranty cost. Our customers expect us to find the correct problems in the shortest possible time and at minimum cost. We owe our customers the best possible service. The purpose of this program is to give you, the technician, an overview of the process of hydraulic system troubleshooting and repair. We'll demonstrate the most common types of problems encountered by Kubota technicians. The procedures demonstrated in this video will help you locate just about any hydraulic problem you may encounter. After completing this program, you'll be better prepared to prevent a misdiagnosis. You'll also save your customer expensive downtime and your dealership time and money. I suggest that before you continue with this program, you review Kubota's Introduction to Hydraulics program and the reference manual provided with this videotape. Without this fundamental background information, advanced service topics may cause even more misdiagnosis. The information in these reference materials will help you find the solutions to the problems in our case studies. Our records tell us most service problems relate to improper maintenance. As you will see, a systematic approach is critical to pinpointing the components causing the problems. Professional troubleshooters have a basic understanding of hydraulic components, a basic understanding of hydraulic systems, a full understanding of hydraulic symbols, a full understanding of hydraulic circuit diagrams, and a full understanding of hydraulic circuit testing and diagnostic tools. Let's take a minute and review our systematic approach to troubleshooting. First, know the system and the components that make up that system. You should also know the path of flow or sequence of events. Study the technical manuals and schematic diagrams of the equipment you're going to evaluate. Never make assumptions or second-guess a system. Second, talk to the operator and field technicians, when possible, to get first-hand information on the machine's history. Third, inspect the machine thoroughly for mechanical and safety problems. Don't forget to remove the keys and tag the steering wheel before starting your work. This is done to prevent someone from starting a machine while it's being worked on and is out of service. Fourth, list possible clues for the problems found in the service manual's troubleshooting charts. Start with the quickest and most obvious things. Fifth, refer to the hydraulic system schematic. Pencil in pump flow and valve opening pressures for later reference. Lastly, you should be very familiar with the test circuits in order to use the diagnostic tools properly. In this VIP service training program, we'll use information from 4 actual cases where technicians failed to follow the accepted standard practices, resulting in unnecessary service time and part replacement. These 4 case studies will provide you valuable experience to strengthen your skills in diagnosing hydraulic system problems. But first, let's review a few safety points. Remove all hydraulic pressure by stroking the control valves. Use only the proper tools. Use a paper towel to find leaks, never your hands. Remember to remove the key and tag the steering wheel to prevent any injuries and damage to equipment. Stop the tape and review the systematic approach to troubleshooting and safety points in your reference manual. Check with your instructor before going on with the program. Now let's see if we can solve the following case studies. In our first case, a technician examined a front loader with a slow cycle time. As we review his steps, you should evaluate his diagnosis. Before a technician can make an accurate diagnosis of a hydraulic problem, he must be familiar with the particular system he'll be working on. Hydraulic schematics provide a graphical representation of all the components in the sequence in which they operate. Unfortunately, the technician didn't find the hydraulic schematic for this model loader, so he looked at one for a similar model. Before you start to work on any hydraulic problem, review the manuals and reference materials so you understand that particular system. Studying ahead of time allows a technician to familiarize himself with the machine even before he sees it. In this case, the operator explained to the technician that the 3-point hitch, power steering, and loader functions were erratic at times, and loader operations had been getting slower over the last several weeks. He also told the technician he compared this tractor with others he operates. The technician asked the operator when the problem first started. The operator pointed out that this was the second time it had happened. The first time, at 680 hours, the system gradually slowed down. Then it seemed to correct itself. It also made an unusual noise somewhere around the engine compartment, but the noise went away. The technician asked to see the maintenance records, then checked the number of hours on the tractor, about 930 hours. The operator said he knew he was a little overdue for maintenance, but he'd been working 12 hours a day for the last 4 months. The records also indicated that the hydraulic oil filter was changed at 65 hours, and the next 4 filter changes were skipped until a week ago when all the oils and filters were changed. The technician operated the loader and evaluated its cycle time. He had no trouble establishing the machine's slow cycle time by comparing it to a second tractor in the yard. The technician decided to do a full pump test at the shop to verify the pump's flow rate. Before working on the tractor loader, he tagged the steering wheel and removed the key. To accurately diagnose the pump, you must isolate it from the hydraulic system, so no other component can cause the pump to look defective. This is called a direct pump test. The rest of the system can't work properly if the pump is not generating its rated gallons per minute at its rated pressure. From our direct pump test diagram, we can see that you must first disconnect the pump's high pressure outlet pipe and connect the hydraulic system analyzer. Special adapters are available from OTC to accomplish this procedure. The analyzer measures the hydraulic oil temperature, the pump's flow in gallons per minute, and the pressure developed from restricting the oil flow through the analyzer using the flow control valve. Hydraulic couplers are frequently damaged during service. To prevent damaging any couplers, always use the 2-wrench method to loosen and tighten hydraulic hoses and fittings. For more information on the 2-wrench method, see the reference manual. Now, let's get back to our case study. After the pump outlet fitting and tubing were removed, the technician selected the correct pump adapter from the kit. He installed the adapter, then connected it to the analyzer with a high-pressure hose. He placed the oil return hose from the analyzer into the transmission oil fill port and wired it into position. In this case, as with many tractors, the transmission doubles as the reservoir for the hydraulic oil. The technician first checked the transmission fluid to be sure no one had accidentally filled the transmission with gear oil instead of hydraulic oil. Next, he opened the flow control valve on the analyzer. If the engine is started before the flow control valve is opened, the hydraulic pump could break from excessive back pressure or cause damage to the analyzer. The technician started the tractor and checked the oil temperature. It was a little cool, so he applied a load to the pump to heat the oil. He brought the engine up to about 3/4 throttle and the hydraulic oil pressure up to 1500 psi by very slowly closing the pressure control valve on the analyzer. The technician knew there was no safety valve in the system, so if he closed the pressure control valve on the analyzer too quickly, the pressure would rise too fast and damage the pump. While the technician was waiting for the oil to heat up, he looked at the specifications for the hydraulic pump. He found it to be 7.79 gallons per minute at 0 psi and 7.56 gallons per minute at 2500 psi. After the hydraulic oil reached 120 degrees, the technician increased the engine speed to full throttle, 2700 RPM. He removed the pressure by fully opening the flow control valve on the analyzer and read the flow meter. The technician knew to keep a record of all tests for future analysis. He wrote down 7.6 gallons per minute next to 0 psi. The technician began closing the flow control valve until the pressure reached 1000 psi. He recorded the gallons per minute, or GPM. As the technician increased the pressure at 250 psi intervals, he wrote down the corresponding GPM until he reached the maximum factory pressure rating of 2500 psi. At this pressure, the flow was 5.7 GPM. That concludes the direct pump test. By isolating the pump from the rest of the hydraulic system, we can be certain we're accurately testing the pump. To accurately diagnose the entire hydraulic system, a T connection must be made on the pressure side of the pump. Tapping in at this point allows you to control the flow and pressure during the remaining tests. Kubota has provided a test port in the hydraulic block for this purpose. To set up the T-test, he installed the analyzer input hose T-fitting at the right-hand port on the adapter block. Then, he removed the loader pressure hose. This isolated the main relief valve from the rest of the system. The technician then proceeded to analyze the system's working pressure and relief valve operation. He opened the analyzer control valve, started the engine, and brought it up to 2700 RPM. Then, the technician compared the pump's free flow with no restriction to the pump's full flow rate at the system's maximum operating pressure. He slowly closed the analyzer flow control valve. Starting at 1000 psi, he read and recorded the flow at 250 psi intervals. When the system reached the pilot relief valve pressure, he heard a high-pitched squeal as the relief valve opened. He recorded a flow rate of 5.7 GPM at 2,250 psi. As he closed the flow control valve further, system pressure continued to increase until the relief valve was fully opened. At that point, the flow rate of the analyzer dropped to near zero. Now the reason for that is, when the relief valve is fully opened, the path of least resistance is through the relief valve, not through the analyzer. The technician opened the analyzer load valve, reconnected the loader circuit, and started the engine. After increasing the engine RPM to its maximum, the technician pulled back on the bucket directional control valve to pressurize the system. He read the pump's free flow through the analyzer at 2,700 RPM and released the cylinder spool valve. He compared this T-test pump reading to the direct pump test reading he took earlier. Both measurements at 0 psi were 7.6 GPM. After recording his data, the technician shut down the engine. He was finished with his testing and was ready to study the measurements. From the technician's notes, we see the pump is designed to flow at 7.7 GPM with no restrictions. It tested at 7.6 GPM. We also know that a new pump is designed to flow at 7.5 GPM at 2,500 psi. And the tractor pump measured 5.7 GPM at 2,500 psi. The data recorded by the technician shows a progressive drop in GPM as the psi is increased. Notice that at 2,500 psi, pump flow stopped when the system relief valve fully opened. Try your skills at solving this problem. Turn to the What's Your Diagnosis sheet in the reference manual and write your diagnosis under Case Study Number 1. Put your VCR on pause while you attempt to solve this problem. When you think you have an answer, push play and see what the technician found. If your diagnosis led you to the pump, you are partly correct. The pump test data showed that it was operating at 76%, which is less than the minimum acceptable flow at full pressure. As the gallons per minute fell off from 7.6 to 5.7, the entire system response slowed down. This resulted in a slow cycle time. The real problem didn't lie with the pump. It was caused by a lack of maintenance. Too often, maintenance takes a back seat to production. Remember, in the case of this machine, it was serviced after 1 week's break-in, then left unserviced because the fluid appeared okay. This machine missed 4 filter changes. The oil appeared clean because as the filter becomes clogged, it cleans more efficiently. The operator stated the problem occurred once, then corrected itself. As the filter clogged, the pump efficiency decreased and eventually the pump cavitated. That's the noise the operator heard. The cavitation action ate away tiny particles on the pump. These particles then circulated through the hydraulic system, causing erratic operation of the power steering, loader, and 3-point hitch, and helped to further plug the filter. Eventually, the hydraulic filter safety valve opened, bypassing oil and contamination from the dirty side of the filter to the clean side without any filtration. Metal and other particles that collected on the filter surface washed through the filter safety valve into the system, eroding the pump even further. The difference between full pump flow and stalled system flow indicated spool valve leakage. To further test a valve body for leakage, remove the pressure and return hoses. Remove and label all the cylinder hoses. Slowly apply system pressure to the suspect cylinder hose port with the hand pump. Valve leakage can be observed if oil weeps or runs out of either the pressure inlet port or the return to pressure port. Pressure should hold at 90% system pressure with little pumping if the spool does not leak. Spools under pressure can leak either to the open center port or to the return to reservoir port. If the hose port does not hold pressure, it may have a leaky spool or a defective circuit relief valve that either needs replacing, cleaning, or adjusting. Some relief valves can be easily adjusted by rapidly stroking the hand pump while turning the adjustment screw. The valve is properly set when the needle on the gauge does not rise above the valve's specified setting when the pump is rapidly stroked. Pressure leak down indicates either a leaky circuit relief, a leaky circuit spool, or both. Replacement of the circuit relief is necessary at this point to establish which component is defective. When the tech first realized the pump was only operating at 76%, he should have replaced it and direct tested the new pump before continuing. When you don't have an exchange pump, continue testing using the old pump data as a substitute reference. That way, you can find out if there are any other failed parts. This will minimize downtime, as all parts can be ordered at one time. After replacing the pump, flushing the system, and changing the filters, he repeated the tests and the system checked out okay. He then put the tractor loader through the loading cycle and found it to be satisfactory. Modern machinery operates quickly, efficiently, and inexpensively when maintenance is performed at the prescribed intervals. Hydraulic systems are faithful servants when supplied with an adequate amount of clean, cool oil. Stop the tape and check with your instructor. Complete the key points checklist for Case Study 1 in the Hydraulics Diagnostic Reference Manual before continuing. Let's try another case study. Keep close track of what the technician does. Read the instruments on all the test meters, write down the information, and look for clues. Again, the technician was assigned a repair job where a loader had a slow cycle time. Before he left, the technician did some research. When he arrived at the job site, the loader was at work. So he stopped and watched for a few minutes to look for clues. The technician asked the operator when he first noticed the cycle times were slowing down. The operator explained to the technician that their last job was in the desert during the summer and that the equipment continuously ran very hot. The job had taken much longer than expected, causing them to operate the unit 200 hours past its scheduled maintenance interval. The operator explained that he noticed a burned oil smell when he checked oil levels. A little later, the cycle time of the loader slowed considerably. The operator also remembered that he'd accidentally bumped into a loading dock with the bucket partially curled up just before the problem started. He got off the loader and looked it over, but didn't see any damage. When the job was finished and the loader returned home, they performed all the overdue maintenance. After servicing, the loader still had a slow cycle time. Additionally, it seemed to lose some of its lift capacity. He then took it into the shop for a closer look. The technician pulled out the shop manual and opened it to the hydraulic schematic diagram. He knew that with all the hydraulics on this R520 loader, there were plenty of opportunities to make diagnostic mistakes. The technician saw there were 3 hydraulic pumps: a large pump for the load sensing transmission, a small pump to charge the large pump, and the main pump in the center for power steering and loader operations. He saw that the discharge of the pump went to the priority valve that gives power steering priority over cylinder functions, and that the main system pressure relief valve was set for 2700 psi. Knowing the filter had just been changed, the technician decided it would be best to start the pump to verify both the pump flow and pressure produced. He knew the pump flow determines the speed of the cylinder, and the pressure determines the lifting capacity of the cylinder. The technician then looked up the pump flow specifications. So he wouldn't forget them, he wrote them down. Before getting started, the technician removed the key and tagged the steering wheel, as in case study number 1. He then installed the analyzer inlet hose to the pump fitting to test the pump flow and pressure, just as he had in the first case study. He attached the return hose to the reservoir and wired it into place. While the engine was idling, the technician examined the oil returning to the reservoir for moisture, air bubbles, or signs of burned or dirty fluid. Next, he checked the pump flow. With the pump isolated, the technician measured 14.0 GPM at near 0 psi and 9.1 GPM at 2700 psi, and he recorded those readings. Next, he installed a T-fitting downline from the P port of the priority valve to test system flow and pressure. A second technician stroked the lift cylinder control valve downward to place the weight of the loader on the lift cylinder to develop maximum system pressure. He slowly closed the analyzer control valve to bring the pressure up to 1000 psi. The technician then took pressure readings at 250 psi intervals and recorded his data. When the pressure reached 1950 psi, the analyzer valve was fully closed. He read 10.0 GPM on the flow meter. As he opened the flow meter and shut down the system, he mentally compared the operating pressure and flow rate to the specifications in the service manual. The technician saw the pump flow at 2700 psi was 65% of normal, and the system pressure had dropped to 72% of spec. He decided to change the pump. After replacing the pump, the technician took time to diagnose the failed pump. He examined the parts and noticed scuffing on the wear plates and a dark lacquer coating on all the metal surfaces. The technician knew that very minor scuffing on the low pressure side of the pump is normal, and was satisfied that what he saw was excessive wear. After seeing the inside of the pump, he decided to remove and examine the system relief valve. He found lots of brown, sticky lacquer. He knew that these deposits alter the performance of a relief valve, so he decided to replace it. The technician then retested the system. He was sure he'd solved the problem until he noticed that the system pressure was only up to 2400 psi, about 300 psi lower than he'd expected. The technician saw from the schematic that the steering and priority valve circuits could affect the system pressure if there was an additional malfunction in that area. To make sure, he isolated the loader valve circuit by plugging the hoses going to the valves. The technician knew there was no system relief, so he slowly increased the pressure on the system by restricting the bypass oil until the pressure reached 2700 psi. Observing the pump flow didn't decrease, the technician knew there was no leakage in the steering and priority valve circuits. So he removed the plug and reinstalled the T-fitting. To verify the problem had been solved after establishing the priority and steering valve were good, and there was a new pump and system relief, the technician stroked the lift valve and was satisfied it was fixed when he read full pump flow and system pressure at 2700 psi. Place your VCR on pause while you attempt to determine the technician's oversight. Try your skills at solving this problem. Turn to the What's Your Diagnosis sheet in the reference manual. Write your diagnosis under case study number 2. When you think you have an answer, push play and see what the technician found. If your diagnosis led you to believe the circuit relief valve for the tilt cylinder was faulty, you were correct. The technician did not consider the fact that the system dropped in pressure only when he stroked the tilt cylinder. The technician should have seen that the tilt cylinder has circuit safety reliefs, but the lift cylinder has no safety relief for overload protection. If he had stroked the tilt cylinder, he would have read the specified system pressure on the gauge. Stroking each of the cylinders separately would have told him the tilt cylinder was at fault. After getting advice from his shop supervisor, the technician looked up the loader relief valve setting and found it to be 3,484 psi. When he tested the loader circuit safety relief, he found it cracked open at 2,100 psi and was fully opened at 2,500 psi. The pressure of the relief valve was too low. Pilot operating relief valves are designed to have a cracking pressure at 90% of their operating pressure. This circuit safety relief valve opened at 60%, so there was no choice other than to replace it. Cracking pressure is easy to test. Slowly raise the pressure on the hand pump until the oil starts flushing through the relief valve. This occurs around 90% of the relief setting. Remember, if the cracking pressure increases beyond 10% of the system relief pressure, the system's response will slow down. Also, remember how the loader operated in the hot desert for an overextended service period? Dust had accumulated around the radiator and further compounded the desert high temperatures. The hotter an oil gets, the faster it oxidizes, reducing the oil's service life. As the summer progressed, so did the oxidation of the oil. As the oil oxidized, varnish and gum formed on all the hydraulic components in the system. Remember when the operator hit the loading dock? The power of the loader pushing against the loader bucket pressed down on the piston in the cylinder and caused a spike in pressure to open the circuit relief valve. Because of the lacquer buildup, the valve did not close and seal properly, resulting in a much lower opening pressure. Remember, the system's maximum operating pressure is determined by the relief valve, which opens at the lowest pressure. This could be either a circuit relief valve designed to be set below system pressure, or a defective circuit relief valve opening it too low a pressure. Look closely at the schematic again. Some circuit reliefs are set higher than the system relief. This is done to prevent external forces from damaging components due to shock pressure caused by equipment bouncing when traveling, or compression shocks, such as hitting a stationary object with the valve in neutral. The maintenance schedules suggested by Kubota are for normal operations. In operating conditions such as we saw in this case study, maintenance intervals should be shortened to maximize the service life of the unit. Kubota, like any other company, depends on professional technicians like yourself to keep equipment running at its peak performance levels to keep customers happy. Stop the tape and check with your instructor. Complete the key points checklist for case study 2 in the Hydraulics Diagnostic Reference Manual before continuing. Let's look at another case study. Before we start, take out your Hydraulics Diagnosis Reference Manual and turn to the Kubota L35 hydraulic schematic. Put your VCR on pause and take a few minutes to look over the hydraulic symbols and follow the oil flow paths through the different circuits. As the technician works his way through the diagnosis and repairs, keep in mind the circuits that you just studied. The operator in this case study complained that all hydraulic functions seemed slow and low on power. He had purchased the L35 at an estate sale and didn't have any maintenance records. Keep close track of what the technician does. Read the gauges and the test meters, write down the information, and look for clues. The technician started by studying the hydraulic circuit. Not having any service records or operation history from which to gather clues, he thought he should begin with the pump. He saw there were two pumps. The first pump was for the hydraulic power steering. The second pump appeared to feed the backhoe and loader. The technician traced this pump's output and located the system relief valve. He noted that this is the pressure control point for the three-point hitch, loader, and the backhoe. He also noticed that three of the backhoe spool valves have pairs of check and pilot reliefs and anti-void valves. Thinking he understood the system, the technician decided to test the backhoe. Seeing the system was already warmed up, he proceeded with his testing. With the engine running at full throttle, the technician pulled back on the boom lever to lift the boom as fast as possible. He was looking for two things: how fast it lifted, and if the engine labored from a lack of power. He didn't notice much change in engine RPM, but he definitely saw that the boom came up too slowly. The technician felt the low power was not the engine's fault, so he decided to do a direct pump test. After completing his tests, he found the pump was only delivering 7.0 GPM instead of the 10.8 GPM spec. That's 65% of the rated flow. He thought the low flow rate certainly indicated a bad pump. So he replaced it. Next, he decided to measure the system pressure by making a T connection at the loader valve inlet pressure port. Because of the technician's experience, he knew he must use a circuit which didn't have a circuit relief to perform the T test. So he used the bucket circuit. He stroked the bucket lever and then slowly brought up the pressure. He read 1800 psi. Knowing the system pressure should be 2500 psi, he was sure the system relief valve was bad. So he decided to change it. Just to make sure he'd fixed the problem, the technician tested the system pressure once more. He measured 2500 psi, right where it was supposed to be. Feeling good about his ability to correct the problem, he decided to fold up the backhoe and put the tractor away. The technician looked surprised when the boom was still operating too slowly. He looked down at the pressure gauge on the analyzer and, to his surprise, saw it was at 1950 psi. Now he was really confused, so he tried something else. He put in the boom lock on the backhoe. Then he pushed the boom lever back to check the second relief valve, and sure enough, it read 2500 psi. The technician knew the answer would be found on the circuit diagram. He saw the boom and dipper stick control valves had their own relief valves, then noticed the loader bucket spool valve did not. Looking up the opening pressures of the boom and dipper stick relief valves, he saw they were both higher than system pressure, about 3400 psi. That's it, he thought. The boom relief valve on the extend cycle was good, and the relief valve on the retract cycle was bad. He decided to replace the one boom circuit relief valve. Performing one last test to assure himself that he'd found the problem, the technician pulled back on the boom cylinder lever. The boom still came up too slowly, but when the piston bottomed out, the gauge read 2500 psi. The technician was now totally confused. He asked himself, if the pressure is okay and I just put on a new pump, why is the boom so slow? The technician had carefully analyzed the system and found several failures, yet the problem still existed. Try your skills at solving this operational problem. Turn to the What's Your Diagnosis sheet in the reference manual and write your diagnosis under Case Study number 3. Put your VCR on pause while you attempt to solve this low-power problem. When you think you have an answer, push play and see what the technician found. If your diagnosis was that the problem involved the hydraulic oil suction filter located under the operator's foot platform, you are correct. All oil entering the system must first pass through the suction filter before entering either of the hydraulic pumps. Quite often, the hydraulic filter is overlooked by both maintenance and repair technicians. Unless an adequate flow of oil can pass through the pump's suction filter, sufficient flow cannot be developed by the pump, and everything downline from the pump will show a slow or weak response. The technician made 3 unwarranted assumptions. First, he assumed the filter was good, even though there were no maintenance records. Second, he assumed from his flow test analysis that the low pump flow was the fault of the pump. And third, he didn't flow test the new pump. If he had, he would have discovered that it performed no better than the original pump. Granted, the relief valves did need replacing, but that would have been much easier to spot if the system's pump flow had been normal. System relief valves can be adjusted if improperly set at the factory. In this case, it was off by over 500 psi. If a relief valve is incorrectly set at the factory, Kubota recommends replacing or adjusting it. This procedure will prevent follow-up service calls. Oh, one last thing. Why didn't the technician hear any cavitation noises? Because the back hole was warm from use before the technician started working on it. Any cavitation noises from cold oil had disappeared as the hydraulic system warmed up prior to his tests. The technician had his hands full with this tractor. When he found there were no maintenance records and all hydraulic functions were slow, this should have been a clue. He would have been wise to perform all maintenance operations before he ever started testing. If he had done this, he wouldn't have replaced a pump that was still good. Stop the tape and check with your instructor. Complete the key points checklist for case study 3 in the Hydraulics Diagnostic Reference Manual before continuing. Let's try one last case study. That doesn't happen very often, but the net resulting damage could be the same in any hydraulic system you might be working on. In this situation, the operator complained that the dozer blade kept dropping. The technician first inspected the maintenance and repair records. He asked the operator why the hose in the dozer blade had been replaced at 150 hours. The operator explained that the dozer hydraulic hose got caught on an old steel fence post that was barely sticking out of the ground and ripped it off. The technician checked the workshop manual and studied the hydraulic schematic. He filled in his pump and system specs on his worksheet. He removed the key from the tractor and tagged the controls. After establishing that the suction filter had recently been serviced, the technician did a direct pump test and recorded 5.2 GPM. The test results showed no problem with the pump or suction filter. Next, he installed the T-connection hose into pump number 3 to analyze the dozer system. He measured both system pressure and pump flow with both the swing cylinder and the dozer cylinder fully stroked. He compared the flow measurements at system pressure and found less flow in the dozer cylinder circuit. That indicated there was internal leakage in the dozer circuit. The technician knew there were only 2 components to the dozer lift circuit that could be at fault: the spool valve or the cylinder piston seal. The schematic told him there was a relief valve in the dozer circuit. The technician lifted the blade to see how fast it would creep down when the engine was shut off. Sure enough, it did settle rather quickly. After a few minutes, the technician thought, if the blade crept down, the piston seals were leaking. The technician decided to ask the shop supervisor before proceeding. Did the technician make any assumption that wasn't true? What advice do you think the shop supervisor gave the technician? Try your skills at solving this diagnostic problem. Turn to the What's Your Diagnosis sheet in the reference manual and write your diagnosis under case study number 4. Put your VCR on pause while you attempt to solve this operational problem. When you think you have an answer, push play and see what the technician found. If your diagnosis was leaking piston seals, you are not correct. When the operator changed the damaged hoses, he failed to thoroughly inspect the new parts before installing them. His carelessness introduced dirt into the system and caused the dozer valve to be damaged and to start leaking. The correct diagnosis to this case study was that dirt got into the anti-void check valve, located in the blade control valve, preventing it from sealing, which added to the blades settling down. To verify the piston seals were leaking on the dozer blade, the technician could have easily tested the piston using the excavator's hydraulic system. Before doing this, pay attention to all safety factors. To leak test the blade cylinder, first remove the cylinder rod pin and lower the rod cylinder. Start the engine and retract the cylinder. Shut down the engine and lower the rod cylinder the rest of the way. Start up the engine and fully extend the cylinder. Then shut the engine off. Remove the hose for retracting the cylinder and plug it. On the KX series, it is necessary to plug it for a valid test. Start up the engine, stroke the blade valve to fully extend the cylinder, and apply system pressure to the cylinder for 15 seconds. Observe any oil dripping or flowing out of the cylinder. Minor dripping may not be cost-effective to repair. When oil flows past the piston seals, the cylinder cycle time will be slowed down, requiring repair and replacement of the cylinder. Quite often, technicians think the cylinder will creep down if the piston seals leak. However, this is an incorrect assumption. For example, when a piston is extended halfway, there is less oil volume on the rod side of the piston than on the open side. It would be impossible to put the larger volume of oil into the smaller space. Therefore, the piston cannot move. In fact, because of this difference in volume, the piston cannot go down even if the piston seals are removed. To prove what we just stated is true, we removed the piston seals out of the boom cylinder, reinstalled the piston and rod, raised up the boom, shut down the engine, and plugged the ports. 1 hour later, the boom was still up where we left it. Another excellent technique in determining the cause of cylinder or valve leakage is the use of the hydraulic analyzer. As a general rule of thumb, if a circuit has leakage in only one direction, it is usually the directional control valve. If it leaks in both directions, it is generally the piston seals. So, that takes care of our last case study. Don't forget to check with your instructor and complete the key points checklist for case study 4 in the Hydraulics Diagnostic Reference Manual. During our time together, I've talked about 4 case studies. The diagnostic mistakes shown in this program happen quite often, especially when a systematic approach to troubleshooting is not followed. To avoid costly mistakes, refer to the hydraulic schematic, use the correct diagnostic tools, and follow a logical, pre-planned diagnostic system. With a little experience, as well as following standard practices and procedures, you can solve just about any service problem. We know at Kubota that when a tractor is well maintained, it will perform quickly and efficiently. Parts will last longer and provide better service. Scheduled maintenance should be performed on time, every time. I hope this program helps you become a Kubota Service Pro. Be sure to watch for our next service training program. I'm Doc Kubota, and I'll see you next time on the Kubota Video Network.